Okay. Well, thank you, everyone. Thank you for the introduction. As you said, this will be a talk about computing excited states with quantum Monte Carlo and its applications to neural network wave functions. So this was joint work across many institutions, not just my collaborators at DeepMind, but also Simon, who was an intern, and Halvard, who I help supervise at Imperial. But yeah, this is going to be a talk about computing excited states from first principles, so a bit similar to Nicholas's talk this morning. This is about really getting down to kind of the basic, the low level, solving the Schrödinger equation directly for arbitrary Hamiltonians, and going beyond the ground state to energies other than the lowest energy. So this has lots of applications, mostly in phytochemistry. Of course, in the last talk, there were some very nice discussions of what you can do with excited states as well. But this is relevant for photocatalysis and photoswitching and band structure and condensed matter. And because the methods I'll be talking about are fully general, you can even apply this to nuclear physics as well. So just swap in a different Hamiltonian, look at nucleons instead of electrons, and you can compute nuclear excitations. And also, while we're here in Sweden, next week we'll be celebrating the Nobel Prize for Research on Quantum Dots, the properties of which all come down to the excited states of these as well. So clearly a highly important area of research. So what does this have to do with machine learning, though? If you look at sort of the intersection between methods in deep learning, which in a sense is the study of how do you optimize functions by stochastic gradient descent, how do you optimize high-dimensional functions by stochastic gradient descent, and methods within computational quantum physics, where you're trying to directly, especially wave function methods, where you're trying to directly solve for the full solutions to the Schrödinger equation. What ends up sort of in the middle of this Venn diagram is variational Monte Carlo methods, right? So where the objective function you're trying to minimize is not, say, some supervised learning loss, but the energy of the system. And there's been a line of research in the last several years of myself and Nicholas and many others who've been looking at using deep learning to increase the accuracy of these kind of classic computational variational methods, where we're really focusing on, as you heard in the last talk, in the space of methods where you sort of trade off between accuracy and speed, looking at the bottom left corner where you're trying to get sort of methods that were not very accurate historically, and make them significantly more accurate by using much more general neural networks as function approximators. Okay, and there are some differences between this sort of classic approach to variational Monte Carlo and this neural network Monte Carlo, neural network variational Monte Carlo, that gives you sort of means you have different design choices when you're doing this optimization that maybe leads to some issues that you don't have with classic VMC. Typically, you would try to make the problem as deterministic as possible, so you would accumulate gradients and expectations over many steps. But in deep learning, you're typically actually optimizing things from very small batches, which might be very noisy, but doing a very large number of parameter updates. So rather than just having a few hundred variational parameters to optimize and doing maybe a few hundred steps of stochastic reconfiguration or something like this, you might have millions of parameters and hundreds of thousands or millions of optimization steps. Okay, so just I'll start with a quick review of what variational Monte Carlo is. So you're basically trying to, at least in ground state VMC, you're trying to minimize the energy of a system, which you can write if your wave function is unnormalized. You can write this out as the Rayleigh quotient, which you can express both the numerator and denominator in a stochastic form here as Monte Carlo estimators, where you're sampling from arbitrary distributions Q. But this will lead to biases in your estimates because you're basically taking the inverse of an empirical estimate of the term in the denominator of the normalization factor. However, if you specifically sample from psi squared, which even if it's unnormalized, you can do that by Metropolis Hastings and things like this, then this bias term will go away. but only if you sample from psi squared. So this is the natural choice of sampling distribution for ground state VMC. And then you end up with this, this expression, psi inverse h psi, which is evaluated at specific configurations of your walkers, and this term inside the expectation is known as the local energy. So for excited states, we need to somehow generalize this Rayleigh quotient from something for the ground state to something for a whole range of excited states. And one natural way of doing this is basically to turn these scalar quantities into matrices. So you replace the denominator with the overlap matrix, where you compute the psi I, psi j integrals for all different pairs of states, because now you're actually trying to compute k excited states instead of one ground state. And similarly, you compute a Hamiltonian matrix for all pairs of states. And then if you take the trace of this matrix, of the inverse overlap matrix times the Hamiltonian matrix, this gives you an objective function where the solution will span the k lowest eigenfunctions. But this is actually invariant to taking linear combinations of in the same way that the Rayleigh quotient is invariant to a scale factor, so it doesn't have to be normalized. This generalized Rayleigh quotient is invariant to taking linear combinations, which means even if the different psis are not orthogonal, you can still get, by minimizing this, you can still get at least up to some transformation in the excited states. Okay. So the question then is, how can we apply this same trick for QMC that works with the ground state to this generalized Rayleigh quotient? So first I'll just sort of briefly review how people approach this problem at the moment and what some of these limitations are. So there's kind of a whole zoo of different, a whole taxonomy of different excited state methods for QMC. They all have sort of different advantages and disadvantages. They largely break down into state targeting methods, where you're trying to compute just a single excited state, or state averaging methods, where you're trying to compute all of the bottom k eigenstates. So, of course, state targeting methods are nice because they're generally computationally cheaper because you're only looking for one state, whereas state averaging methods give you a more complete picture. So if you want to say, look at the dynamics of a system where the initial energy is below some threshold, then you actually need to compute an entire range of states instead of just one. Okay, so for state targeting methods, you can look at, say, energy targeting, where you look at the lowest state above a certain energy threshold, but then you might need to know what that threshold is. You have what are called root targeting methods, where you're just looking for the second or the third or the fourth excited state, and you have to compute these. Does the pointer work here? Yes. So you have to compute these. Again, these Hamiltonian and overlap matrices, basically from noisy samples, and then solve this generalized eigenvalue problem. And this can sometimes suffer from root flipping, where you jump between different solutions. It's not guaranteed to converge. You can look at symmetry targeting, where you might know certain symmetries of certain excited states. And so you just look at the lowest energy state that has the particular symmetry that you care about. But of course, that only works if you know the symmetry you care about, and if the state you care about is the lowest energy one. Among state averaging methods, most methods that people use today assume that the different states are orthogonal and are taking, again, they're minimizing a weighted sum of the energy of different states. The most common methods, basically, you have to assume a certain functional form, like a Slater-Jastrow ansatz. So it might be a sum of determinants that share a multiplicative Jastrow factor to account for cusps. And then the math works out nicely, although you still have to compute these noisy estimates. So as I said, if you're working with deep learning, first of all, deep neural networks don't obey this functional form. And secondly, if you're computing things from small batches, you'll get very, very noisy estimates of both of these, and the statistical bias will basically kill your optimization, so this won't work. What people have tried in combination with these neural network methods is penalty methods, where you just add an extra term into your optimization, where you say in addition to minimizing the energy, we also want to have a penalty, something like the cosine distance between the different states that pushes things apart. And certain variants of this can be unbiased, but sometimes you have issues with states collapsing onto one another, or if you make the penalty stronger to really push them apart so they don't collapse onto each other, then if you pick a nonlinear function for f here, this then becomes, you then get biased estimates. So you might not get accurate optimization, but we have developed a new method that we're calling natural excited states, which avoids pretty much all of these pitfalls. Okay, so again, the starting point for this is this matrix form of the Rayleigh quotient, and as I said, there were kind of two problems that we need to solve. One is, can we generalize this Monte Carlo trick to get unbiased samples, and especially unbiased estimates of the gradient here, so that we can optimize our ansatz. And even though this objective function will, minimizing this will give you states which span the excited states, can we actually disentangle them? Can we unmix them so that we actually get the energies and maybe observables in order from the ground state on up? And the answer to that is yes in both cases. So the first trick is that we can actually, if we write out this in the right form, we can actually turn this generalized Rayleigh quotient back into a Rayleigh quotient for the ground state, but for a generalized system. So if instead of looking at an n particle system, you basically look at an n times k particle system, where the Hamiltonian is just the direct sum, where each of these is the Hamiltonian for the problem you're trying to solve, acting on a different state. And you just take, again, the sum of energies here, so it looks a lot like state averaging. And then the wave function that you plug in here, this capital psi, is essentially a Slater determinant made up of individual states. So you're taking the determinant of this matrix, that's all excited states by all configurations of particles. And it looks, as I said, it looks a lot like a Slater determinant, but rather than each entry being an orbital of a single particle, it's an entire many-body wave function. So it's kind of like a Slater determinant of Slater determinants if you use a Slater determinant ansatz, but it's a Slater determinant of wave functions. Okay, and you just sort of grind through the linear algebra, and you find that these two expressions are equivalent. And the nice thing about this is that, as I said, even though the individual psi 1 up through psi k, even if these are not orthogonal, if these were to collapse onto the same state, then you would have basically two columns would be the same in this matrix, and the overall expanded wave function would be 0. So writing things in this form actually prevents things from collapsing automatically, even though you're not assuming anything is orthogonal. Okay, and then we can basically just do the same standard ground state VMC trick, plugging in, basically sampling from this capital psi squared. The math works out very nicely, and again, you grind through a bit of linear algebra, and you recover this generalization of the local energy from a scalar to a matrix, where again, this capital psi is the matrix of all of the individual states by individual particle configurations, and h psi is just the Hamiltonian applied to the matrix, where you apply the single system Hamiltonian to each of these. And it really is, mathematically, it's literally almost the simplest thing you could do is just turning each of these scalar terms into matrices. And you might say this is almost too simple, like, how does it work? But it only works specifically if you sample from this capital psi squared. So this is the natural distribution to sample from for excited states, in the same way that lowercase psi squared is the natural sampling distribution for the ground state. Okay, so that tells us how we can actually optimize this, because you can use all the same machinery for optimizing ground state VMC quite directly. It works pretty much out of the box. But then we still have to actually sort of demix these different states, not get just the total energy, but the individual energies. But that also turns out to be quite simple. So if we have a linear if the psi star are the true optimal excited states we're looking for, and we have a linear combination of them, so what we recover is some linearly mixed version of these. Then writing out this, this local energy matrix, it's clear that the eigenvalues of the local energy matrix are the energies that you're trying to recover. So what we do is we just, we might not have in practice, we might not exactly have the optimal solution, but we just accumulate this local energy matrix over many, many samples from many, many walkers and diagonalize it, and so we can recover basically up to a constant the correct demixing matrix. And then we can basically use the same trick for any arbitrary observable that we care about, and use the eigenvalues from the energy matrix to demix those as well. For on-diagonal observables, that's enough. If you care about, say, transitions between excited states, you might want to compute, say, transition dipole moments. And then for off-diagonals, you have to multiply this matrix by its transpose for various reasons. That means, so you can recover this up to a sign factor, but the sign factor isn't physical anyway. So how does this work in practice? So everything, as I said, so far everything has been fully general. This can apply to any Hamiltonian. I haven't even talked about chemistry, but all the experiments are looking at the Born-Oppenheimer approximation. And so, as I said, you can plug in, you want to compute many, many different ansatzes, many different wave functions, but in practice we just take either the FermiNet or Psiformer, which are two of these neural network ansatzes. It's sort of very similar to the PESNet and globe ansatz that Nicholas was talking about. And actually we just train one neural network, but we just have many outputs. So that helps cut down on the number of parameters that you have to optimize and helps share information between these different states. So just starting with atomic spectra, you're able to calculate things to very, very high accuracy, sometimes something like a 1/10 of a millihartree on many of these. Maybe not enough for a spectroscopist, but for chemists at least, it's very, very accurate. It gets a bit worse on fluorine and neon, but we think that's mostly because of ansatz quality, because as we go from the Psiformer is basically a more accurate version of the FermiNet. It's slightly newer, and going to these more accurate ansatzes, we cut the error down. So pretty much everything is within chemical accuracy, at least. As I said, you might also care about other observables like oscillator strengths, which can be computed from transition dipole moments. This gives you a measure of basically the probability of transitioning between different states. And looking at just an array of small molecules, like from boron hydride up to things like thioformaldehyde and things like that, we're able to get very high accuracy. Our method is in blue, and the lines here are comparison against coupled cluster baselines that have been extrapolated out to the complete basis set limit. One nice thing about what we're doing is we don't need basis sets. If you compare that to some of these penalty methods that I talked about, in black here, you can see the errors are typically much larger, especially for the oscillator strengths, which are quite sensitive to accuracy, even more so than the energy calculations. So we're quite happy with that. We can go beyond equilibrium geometries as well. So we look at the carbon dimer and look at entire potential energy curves there. So we can compute adiabatic excitations, where rather than just looking at a fixed geometry and looking at the energy differences, we can compute the equilibrium energy for each of the different states and look at the differences there. And that matches experimental results quite nicely for most of these states. And we can also, analyze things like we can compute density matrices and so actually try to understand the nature of these excitations. And so this is looking at the occupancy of different orbitals, of different natural orbitals in the different states. And you can see some of these states are single excitations where, the electron here is getting promoted into this orbital, whereas some are double excitations, and also a lot of existing methods for excited state calculations really struggle with double excitations, so it's nice that we get them accurately. We can do conical intersections, matching MRCI results on predicting where the conical intersection for ethene is. this is a classic failure case of TD-DFT methods, and we're even a little bit better at predicting where this is than these neural network penalty methods. But where this really shines is as you scale to larger systems, these penalty methods start to do worse and worse, whereas we remain about as accurate as these very high precision coupled cluster benchmarks. So again, these neural network penalty methods are here in black. So this is without some of these heuristics like variance matching, and this is with variance matching. You can see the error is still on the scale of TD-DFT or CASP-T2, whereas our Psiformer results in green are accurate not just for the first excited state, but up to as many as 5 or 6 excited states. So this is basically the first time that a neural network ansatz has been used to compute excited state properties to this level of accuracy, at least on the scale of benzene. And just finally, just a word on computational complexity here. If you think, we are really looking at methods where we're trying to push accuracy as much as possible, sometimes at the expense of speed. So if you wonder why we stop at benzene, the computational complexity is somewhere between quadratic and cubic. But if you look at sort of standard eigensolvers just for dense matrices, things like the Lanczos method, those scale cubically with the number of eigenvalues you compute as well. So it's not really surprising that you would see this level of scaling. So I'll just wrap up here and say that we've I hope I've convinced you that natural excited states is, as the name implies, the natural way to compute, to generalize variational Monte Carlo to excited states. It works very well in conjunction with deep neural networks, which has enabled, calculations to unprecedented accuracy on larger systems. But it's also more general than that. So you can plug in any classic ansatz you care about and use this method with it. So I look forward to seeing what else people can do with it. And that'll say, the code is available on GitHub as well. And thank you. I'll take questions.
So the talk is open for questions.
Everything was perfectly clear then.
Imagining more complex molecules like transition metal complexes and things, do you see the potential there, or are there bottlenecks to be overcome?
Yeah, absolutely. So there's been some work, I think from like Ji-Chen's group in Beijing, and a few others on adding pseudo-potentials to these calculations. And in fact, actually, some of the examples I shared here, the heavier atoms here, we used pseudo-potentials. So that's actually available in the code online. So you can run this with transition metals as well. We didn't include that in this paper, but people have looked at transition metal complexes with just in the ground state. The Achilles heel of all of this stuff is scaling. So I think there needs to be more work on just sort of good engineering and good approximations to help scale these methods beyond what we've done. But in theory, there's no reason you couldn't do it if you had enough computational resources.
I have a question. Mm-hmm. So how, very interesting you doing excited states. So 2 questions. First one is, how does your approach behave close to conical intersection? And the second question I have is, are there any particular problems associated with doing core excited states?
Core excited states?
Yeah, I mean, you excite out from a 1S, so X-ray spectroscopy.
Well, I mean, this is an example of a conical intersection here, and as I said, we get it about as well. See, our method is in blue, MRCI is in green, so there's a bit of a shift in energies, but we get the you know, the locations of the intersection, all that, you know, just as well as any other method.
I see.
So it seems to work there. We haven't looked at core excitations in our experience because, you know, we're not really building in any assumptions about the type of excitation or anything like that because of the generality of the method. I would expect it would work well. If there were sort of some small examples, we could look at that.